Picture a theoretical salad. How healthy is it? How filling is it? How tasty is it? These are all questions that I had recently when I saw my colleague Kalina preparing to eat a salad. I was worried that the salad might not be nutritious enough, in which case I could recommend she go to the doctor. Or perhaps the salad was not filling, in which case I could offer her a bag of chips. So while she was looking the other way, I collected a dataset of all the pieces of her salad. When I laid out my salad dataset, I couldn't easily draw any conclusions about the salad. There was too much information and it wasn't visually organized in a meaningful way. How can we take a dataset like this and make some of its characteristics more visually obvious? One of the neat things about using images to communicate data is that you can encode information in many ways other than labels and text. Visual objects can have lots of visual attributes, sometimes called visual dimensions, that visualization designers get to play with. When I use the term dimension, you might think first about the x, y, and z dimensions in three-dimensional imagery. You can use these dimensions to connect numerical data to objects in your scene. For instance, I can encode my food types by their average size horizontally in my image. The smaller types of food go to the left side of the image, and the larger pieces of my salad go to the right side of my image. Then I can encode each individual piece of food by its size vertically, normalized based on that food type's range of sizes. Another dimension of an image is the size of an object. Here I'm changing the size of each object based on how much nutritional value it provides. Not all image dimensions are created equal. Position and size are directly comparable measurements. One value is objectively higher or larger than another. For instance, if the size of one piece of salad is 2 times the size of another piece of salad, I can take that to mean that this piece of salad has 2 times the nutritional value. But this isn't the case with some other image dimensions. Take color, for instance. Look at what happens if we encode each type of vegetable as a color. Each of the food types stand out clearly as distinct groups. But aside from being different from each other, the 5 colors don't convey any kind of inherent measurable difference. Is blue more or less nutritional than yellow? You can't tell by looking at this image. However, you can also encode color to equate to a range of numerical data values that have a defined low and high. Assigning color to scientific data is done through a process called color mapping. Color mapping is one of the most crucial aspects to scientific visualization because colors are used to indicate numerical values within the data. Color mapping is the process of assigning color values to data. For instance, this is a version of my salad data where I am mapping color to size of pieces of salad. And this is a version where I'm mapping color to protein content. These 2 different data-driven color treatments give you different insight into the data. Color mapping is done using a set of mathematical operations called a color transfer function, which consists of 2 parts, a data range and a color ramp. The range tells your transfer function what minimum and maximum values to consider for a particular data attribute. Let's consider a more likely scientific data set, our local neighborhood of stars. These stars have a temperature attribute that's measured in units of Kelvin. You can see that starting with a range of 0 to 1 for this set of stars gives us absolutely no variation. That's because the data range is in the realm of thousands of Kelvin. Now, when we change the range to be from 3,000 to 12,000, suddenly we see different colors across the data. The second part of a color transfer function is the color ramp, like this blackbody color chart. When I apply the blackbody colors to the range we selected, you can see a lot of interesting color variation across this star data. Each color on the color ramp lines up with a corresponding position in the data range. In the blackbody color ramp, a data value of 3000 Kelvin gets a red color from the far left edge of the color ramp. A data value of 7500 Kelvin gets a white color from the middle of the ramp, and a data value of 12,000 Kelvin gets a blue color from the right edge of the ramp. Not all color ramps have to represent physical light. They can be as simple as 1 solid color, or they can have 1,000 explicit colors. Most color editing tools automatically fill the spaces between your chosen colors with some interpolation scheme, though, so you won't need to be that specific. Many visualization tools come with color ramp presets with names like Cool, Cool Warm, Pastel, and Doom. Some of these presets are better and worse for certain purposes. A common piece of wisdom is that the rainbow color map is usually a poor choice. Because the rainbow colors cycle, there's no clear high or low end. Because the human eye is more sensitive to brightness than hue, it's usually recommended to have a consistent change in brightness from one end of the color ramp to the other as well. You may find yourself a bit concerned about the freedom color mapping gives you. If you were given a dataset of galactic clouds, you could make the clouds green or orange or black. Is it wrong to choose colors just because they look nice? It is vital that your color design have some rationale. Many visualization designers prefer to include a graphic element called a color bar on top of their visualization, like in the soy plant heat map video. A color bar shows the color transfer function's range and color ramp so the audience can analyze the data more thoroughly. But the fact is that even the most photorealistic science imagery you're used to seeing is not showing real colors. Take for instance this Hubble image of the Orion Nebula. Its beautiful pinks and blues work in perfect harmony. But actually, this would all look like a wall of green to the human eye. This is because the human eye is less sensitive to visible color than the Hubble telescope. The lovely pink and blue colors were chosen to emphasize features, to inspire audiences, and to show us things we wouldn't see with our own eyes. After all, why should we stick to what the human eye would see when we have the technology to show something more clearly than the human eye would see it? Similarly, in images where atoms and molecules are represented as colored shells, the color is completely invented. In the real world, the colors we see are the result of light bouncing off objects and hitting our eyes. But atoms are not actually solid surfaces that reliably bounce light back at us. The colors in the visualization are chosen by designers to guide our eyes and tell a story, not to represent an impossible standard of physical realism. Color transfer functions are just one special type of transfer function. All a transfer function really is a method to turn a numerical attribute into a visual attribute. Another visual attribute that can be controlled in the same way is transparency. Let's go back and take another look at our salad data. If I connect sugar content of each vegetable to its object's transparency, you can see the sweet carrots stay fully opaque, but the sugar-free lettuce goes almost invisible. Unlike color, an object's transparency is controlled by a single number, something between 0 and 1, where 0 is invisible and 1 is fully opaque. Because transparency is a scalar instead of a vector, when we design a transparency transfer function, we use a one-dimensional spline ramp instead of a three-dimensional color ramp. In this dataset, we can see a spline ramp mapped to transparency. In 3D volumetric data, we refer to transparency with the term density. You can see that when the spline ramp is set to a constant value, that every voxel in this volume is the same density value, and the whole domain of the volume looks equally filled in. But now, if I create a linear mapping from 0 to 1, you can see that the shape of the data emerges. Any voxel that has a data value below our range maps to a density of 0 and disappears. Any value above our range maps to 1, and it's completely opaque. And everything in the middle of the range gets some amount of translucence and reveals interesting details. But your spline ramp can become much more interesting than a simple linear mapping. In this dataset in particular, I want to emphasize the spiral arms of the spinning disk, and I want to clear out a hole in the middle of the disk so that I can place a star there. You can see that by adding nodes to the spline, I clear out the excess outside gas, I reveal the spiral arms, and then I keep the density low until it gets near the center in order to really emphasize the center hole of the disk. For other one-dimensional visual attributes, we use spline ramps as well. For example, we can use a spline ramp to create three-dimensional geometry from a two-dimensional image by changing the height of a surface based on the pixel data. My range for this height transfer function is 0 to 0.5, which means black maps to 0, and any color brighter than a 50% gray gets treated as the highest value in the ramp. As I change the maximum value of height displacement, you can see how the brightest regions of the image get raised up from the flat surface. This is what happens with the default linear mapping, but what if this region is not what I'm interested in emphasizing? One method we use for finding regions of interest is to create a bump in the spline ramp and drag that bump across the range. You can see that as I drag my bump, different regions of the image poke out. I'm going to choose to emphasize the arriving plasma instead of the bright turbulent area. I'm also going to choose to smooth out the spline ramp so the height change is less sudden. Advanced transfer functions can include more mathematical manipulation as well. For instance, applying an exponent to the attribute values or multiplying two separate attributes together. Trying to pack as much information as possible into every dimension of the image can make a visualization overwhelming, especially to an untrained audience. For instance, this visualization has so much going on that it's difficult to interpret. There's color, height, three-dimensional position, shape, surface area, volume. All of these are making it very difficult to understand the point. Especially for outreach visualization, repetition can help your audience. That's why when working with our original salad dataset, it's good to reinforce information by repeating it, by making both the shape and the color of the objects reflect the food type we're looking at. While I could encode yet another data variable into the shape of the objects, that would be a lot of information for an audience to take in, and maybe it's information that isn't especially important in our specific investigation anyway. There's one more image dimension I want to leave you to think about, and it only works with moving images. It's motion. You can see in this visualization, as stars move across the scene, that they have different relative speeds. The speed is a data variable that has been encoded into the motion of the movie. I can encode motion into this salad data as well. Now the speed of each object wiggling is related to how much energy it provided to Kalina. Now we can easily see that Kalina got plenty of nutrition and energy from her salad. The only thing she didn't get enough of was sugar. Fun fact: some people are much better at understanding certain dimensions than others. Area is one of those tricky dimensions. For instance, what do you think has more pizza? One 18-inch pizza or two 12-inch pizzas? It turns out the 18-inch pizza does.